although they improved Siri a great deal. Anyways, the 24th, you had a Nearpod, and one of those, and I'll get my iPencil charged in just a second. That 24th on that Nearpod had to do with the chemiosmotic gradient. And it specifically spoke about the use of chemiosmotic gradient in cellular respiration. You can turn the lights off now if someone would. And photosynthesis. And that's what this whole week is on, cellular respiration and photosynthesis. That's your unit. And you see that the test, when the test is, if you flip it to the back of your syllabus, you see the test is on Monday, January 31st. There's some key little things you want to make sure you're focused on when you're studying this material, because there's a lot of vocabulary words in the study guide, a lot of things we will talk about today. We're going to talk about them, we're going to identify them, and then you're going to study them. So that's what we'll be doing all week. Okay, so you got to make sure you know these. My strong suggestions: you do note cards to try to get some of these words straight in your mind. The very next thing we're going to do is the cell cycle, and we're going to do mitosis, meiosis. It'll be next week, the whole week. We're going to be doing that, and that unit will have a test at the end of that. And then we'll talk about, I'll you know what, I'll come up with a plan for you and I'll draw it out. But anyways, short term, just so you stay focused, these are the big three things you're going to need to know. How is the chemiosmotic gradient used in cellular respiration and photosynthesis? And the key is, how do we make ATP? And you saw that in the Nearpod. So we're going to talk about it today in detail. So ATP. This is the key. I hate not having my iPencil, but this is the key energy form for your cells. For all life on Earth, as far as we know, life on Earth uses ATP as this energy source, as the currency, as the thing that drives chemical reactions in your body, as the things that drive chemical reactions in every living thing. However, there is a rule, and it's still on the board, I believe, yeah, it is. There's a law of thermodynamics, the first law. It's really the fundamental law that drives almost everything in chemistry, in biology, in physics. It's the law that says you cannot create or destroy energy. If you remember that and then you apply it, it's hard not to understand what every other law, every other rule in science comes from. Most every other rule in science comes from, rooted in that law. So ATP is, that's why you balance equations, for instance, is the first law of thermodynamics. You have to balance it, because if you're not, you're saying you're creating energy or you're creating matter, and we can't do that.
Bless you.
Yes, bless you. So ATP is the energy that we use in the body, but where do we get ATP, right? Where does ATP come from? And so you have to, someone want to close that door? Thank you. So you have to wonder, where does ATP come from? Well, there's two different sources depending on what kind of beastie you are, what kind of life you are. There's basically two, all life needs this stuff. You need it. How do you get it depends on what you are. So if you're what we call a heterotroph, I hope the pencil's working because I hate writing with that. If you're a heterotroph, all right,
Yeah.
I don't forget it, man. I'm trying to write and think, and I'm doing multiple things going on, and that's never a good idea, but this job that requires it, so. Heterotroph, or you're an autotroph. Exactly, you got it.
I remember that.
You should, I hope you do. You should have learned this in middle school, yes. Heterotrophs, here it is. Here's the thing about heterotrophs. If you didn't, that's fine. You're learning it now. Write it down. It's a vocabulary word. Heterotroph means things that eat. That's it. They eat their food. These things have to in some way ingest it. They can't make it. Autotrophs make their own food. They eat too, but they don't have to ingest it. They don't have to hunt. These guys have to hunt or search or in some way find the food. All right. These guys make their own food. They don't need to do all that. They make their own food. Autotrophs are plants, but it's also there are plants and bacteria and some plants, bacteria are the two main kinds of autotrophs that are out there. Plants obviously being the big one. And this is the key one that a lot of you have learned about. You've learned about plants, but some bacteria also do photosynthesis, which is the way that you make your own food. There's two ways to make your own food. There's two ways, and the one way is the biggest way on this planet anyways is photosynthesis. The other way is something called chemosynthesis. All right. It's not as important to life on this planet, at least on the big scale. When you look at the mass of life really depends on photosynthesis. But chemosynthesis is important. At the very bottom of the ocean, in the crust of the earth where no sunlight exists, life still exists. There are places in the deep volcanic underpinnings of the planet where there are tiny bacteria that grow using chemosynthesis, and those bacteria then feed other organisms that feed other organisms, and you get a whole ecosystem down at the bottom of the ocean near these volcanic vents.
So chemosynthesis really works at the bottom of the ocean?
But that's one place. There are other places, but that's basic. Anywhere light doesn't happen.
So
Anywhere in the dark. Life still happens. Life is an amazing thing to study. So when we're looking at ATP, life needs to make ATP. How it makes ATP can be, as I said, with photosynthesis, or it could be using eating, finding, hunting food. Of course, what do heterotrophs really depend on? They depend on plants or bacteria, right? They eat autotrophs. We eat autotrophs. We are heterotrophs. We hunt and eat our food or grow it on farms. And you might say, well, I don't eat plants. I don't like green stuff. Or, well, you eat fruits, and fruits came from plants, most of you. And any of you that don't eat fruits and vegetables, well, I'm sad for you because you're going to end up being sick. But if you just eat meat, what do you think meat ate to get big? They ate autotrophs. So the sequence is autotrophs are the foundation, are the underpinning. I don't know why.
They know how to do it. They'll be okay.
I know, but I don't want, I'm recording this and I don't want to be the, trying to fit it all in here. Who just came in?
Me.
All right. Hurry up. There's stuff there you need to get, and we started. So autotrophs are the foundation. They're the biggest by mass. They have to be the biggest. If we're going to eat, if everything else depends on it, you have to think about if you're building a building, all things depend on it, then autotrophs have to be the foundation of it. So they have to be at the very base of it. Now, autotrophs have to get their energy from somewhere because we said energy cannot be destroyed or created. We can't create or destroy energy. So where are autotrophs getting their energy?
The sun?
The sunlight is correct. It's the sun. Sends its sunlight to the planet Earth, and without sunlight, autotrophs die because that's their source of energy. They change light into energy, another form of energy, chemical energy. So light energy gets turned into chemical energy. So let me be very clear about this. Every time you switch energy, you only get 10%. You only keep. This is a really important rule. This is how inefficient life is. This is not an easy process. Most of the energy from the sun gets lost to heat. Heat is lost energy. We cannot use it. It does not become a plant. It can't become a plant. So lost energy to heat, we only keep, every time you go up, you only keep 10% of the energy available, whatever it is. Forget the units. I've seen on some problem sets from the state and from SAT or science exams where they actually they tell you numbers and they give you units. It doesn't matter. It's 10%. Whatever you had before, if you had 100 units, 100, on this side, you're only getting 10. So every time you change, every time you eat, you're only getting 10% of that energy. The rest of it's going to waste. Okay?
Wait, is that what they tell athletes to eat more?
Because you're using more of the energy, but yeah, to some extent, yes, that's true. So you're only getting 10%. This is going to be important later. You might want to learn it now and save yourself some trouble, but you need to learn it. This thing where I just drew this box, this is the base of what's called the pyramid, an energy pyramid. We call these trophic levels. So autotrophs are at the base of the trophic pyramid. Is that clear? Everything else on the trophic levels. Then I know you've heard of these before because middle school teachers love them because they're so easy to teach. I say easy because it's not that it's easy, but rather it's a lot more obvious, right? The stuff we've been talking about up to now and the stuff we'll be talking about in a minute is not obvious. Does that make sense? You don't see it. Plants you see, right?
What are trophic levels?
A trophic level is the energy level where you find life, where life is found. So autotrophs are the base of the pyramid. So so a trophic level is the, well, you'll see, you'll recognize the next one. The next one is, they're called primary what?
Source.
Consumers. Do you remember those?
And then secondary consumers.
That's right. Then there's secondary consumers. It goes,
And then decomposes, right? Or no?
kind of. Secondary consumers. And then, obviously, tertiary consumers. I'm not going to write it out. But at each trophic level, what happens if this is the autotrophs at the base, you only get 10%.
So it started at 100, then it went to 10.
So that's right. So if this was 100, this is
30 from 30?
this is 100.
Third.
This is only 10. This is Up here, you only get 1, and this is 0.1, right? So that every time you go up, so that limits us, right? That limits us. So if you have, let me ask you a question that I've seen some people ask. If you had 1,000 plants, how many primary consumers, if it was a 1-to-1 relationship, how many consumers could you possibly have? Could you have 2,000 consumers if you had 1,000 plants? 1,000 units of plants, could you have 1,000 units of cows? No, it takes a lot more to feed the cows. So you need to have a lot more plants than animals. So when people say, why do we need plants? Why can't we just build cities everywhere? Well, consider if you're going to have 9 billion people on the planet, you need to have, and you're going to have people eating meat, then you need to have people eating there have to be a lot of plants to feed those cows, and then you have to feed because we would be what? Secondary consumers at that point, right? So if you're going to have 9 billion people, let's call them units. Some kind of community alert. It's probably Parma.
Why do you get farmed?
My brother-in-law lives in Parma. My brother's in a home in Parma, so I gotta make sure I know what's going on. I don't know.
Smart.
So, anyways, at each level, you're going to lose 10%. So this influences ecology. It influences biochemistry. The bottom line is that the law of thermodynamics says that if you're going to lose, and we know that there's no efficient system, we're losing 90% of the energy at each level, then we have to have a lot more plants than we do cows, and we have to have a lot more cows than we do humans. So that's why people say you might as well just eat plants and you save this primary consumer. We're not losing as much. We don't need as much land. We don't need as much water. So that's where the idea comes from. It's rooted in fundamental science. So those are your trophic levels, and that's your energy. So now let's talk about the paths, right? How is it that we get ATP from plants, and how do plants take sun, that's light, and change it into sugar? Because that's what they do. They take that light and they turn it into sugar, the stuff we eat, the stuff you're sitting on, right? Because that's a plant. You're sitting on a plant, on what's left of a tree. You're sitting on a tree that's made of sugar, and you're sitting on it. How is it that started off as sunlight? That is an amazing thought, isn't it? That sunlight got magic. Like, you guys watch these magic shows, don't you? No. Did you grow up watching Wizards of Wizardly, whatever?
Oh, Wizard of Waverly.
Whatever. When you were little kids, you were sitting in front of the TV, and you watch those shows, and you love, the cat turned into human, and you turn this into that. Everybody's like, yay! But then you're in science class, or I don't know if you watched Harry Potter or whatever. They make things appear and disappear. They make things happen. But here we have magic happening right in front of your eyes. Science tells you that we're taking light and we're turning it, not we, but plants take light and turn it into sugar, into themselves. And we somehow are not impressed by that. That to me is
mind-boggling.
It's a lack of imagination sometimes, I think. Imagine that you're taking light, which is, you can't touch it. You can feel the heat, you can see the light, but you can't touch it. But you're taking that light and you're turning it into something not only that you can touch, but that you can eat. And we use it to build our homes, and we sit on them. And we use that light was turned into these chairs with work, unlike the shows, but with still amazing magic, in my opinion. It's not really magic, it's science, but the point is that I'm equally impressed. And I do like those magic shows and movies. So in any case, let's take a look at this idea of photo. Photo means what? Says what? Yeah, people think that photos don't mean pictures. The word picture comes from the word photo. Photo, we use photo for, it's actually the word is photo is short for photograph. What's a graph? A drawing, right? Or it could be a picture, right? It could be a picture, right? But it's some kind some kind of representation, right? A graphic is some kind of representation. So a photograph, right, is a picture of light. It's a drawing of light done on a film or an electronic source. So when we use the short photo, really what we mean is a light drawing, right? So photo means light. That's what it means. And then we have this, the second part of the word, which is synthesis. So synthesis means make. And we should know this one already because we've talked about synthesis, protein synthesis, and we've talked about RNA synthesis. So we talked a lot about this already. So photosynthesis. So you have to be able to take this photon. This is called, by the way, a particle of light. Did you know light acts as both a particle and a wave?
Yes.
All right. So light acts as both particle and wave. And a particle of light, and when I say particle, you have to think of like the dust in the air. When you look through a light beam, look through the sunbeam there coming through the window, you see those little particles? Those are particles of dust. Well, there's smaller particles of light that fill the room. When you look at a light source, you're not looking at one light. You're actually looking at billions upon uncountable number of little particles of light called photons.
I've never heard that phone.
Really? That rings a lot in the afternoon. Mr. Mendoza's room, may I help you? Hey. Madison Hampton? I don't have her first period. I haven't seen her since the beginning of the year. I haven't seen her. I'm sorry. I see her in class, but not in the morning. All right. All right, bye-bye. So photons are particles of light. And what plants do is they capture these photons. They capture them. Now, how do you capture light? Who can tell me? When you're trying to catch light, what do? You do it. You've done it since you were little kids. Well, no, you can't do that. I mean, it'd be nice. Say that again, I can't hear you.
What if you just sit where the sun is shining at?
Okay, well, you could do that. You could sit and you'd feel the heat, but part of you catches light. What part of you is catching light?
Your eyes?
Eyes do catch light, but they're using something. So eyes are the organs that catch light. That's right. Do you remember? I don't want to get any clue I give you is just going to give it away. What catches light? Think about it. I wouldn't be asking you if you didn't know it. If it wasn't possible that you would know it. I'll give you a second to think about it. Something that captures light. If you wanted to catch light. Can't use your hands.
Could it be our skin?
It's in your skin. It's in your skin. It's not your skin, but there's something in your skin that catches light. Yes.
Your skin?
Melanin, yeah, that's right. Melanin catches light. What is melanin? Pigment. Pigments. That's right. That's right. See, I told you knew it. So these molecules in life that we call pigments, we know them. We know them well. I see them used to make hair blue, and I see them to make hair red. I see yellow shirts and tan shirts and blue shirts, and I'm wearing a kind of gold tie, and there's yellow. But these are all pigments. These are, huh?
I sound like your tie.
Oh, thank you. So when you're talking about pigments, all you're talking about is a molecule. It's just a molecule. It could be made of protein. Usually they're made of proteins. A bunch of atoms together. And what happens is that they're shaped, all atoms, we should know this. I guess this is a kind of fundamental thing everyone should know. All atoms have protons and neutrons the way we've discussed. And then you have these electrons that are on the outside of the atom. And this guy that I'm sure you've heard of, named Einstein. Am I right? You've heard of him? Yeah. He's a real famous guy. He's not the only smart guy. There are a lot of smart guys that work this out, but Einstein won a Nobel Prize for this. Is the light, atoms capture light, and because the electrons absorb them, they take them in, and that increases their energy, and then the electrons jump from one energy level. When they get taken that energy, they jump up to another energy level. These are energy levels around the atom, and when they come back down, they release light, but they release light in a different frequency, different energy.
So when they go up, they do what?
When they go up, they're just taking the light in. Then when they come back down to their normal position, they release that light. But they release light in a different frequency. So when it goes in, let's say yellow, it comes out blue. Does that make sense?
What does that say on the inside?
Those are protons and neutrons. I meant to draw pluses and N's, but it just turned into gibberish. So let me erase that. Is that better?
Yeah.
Protons and neutrons. And obviously electrons don't match, and that's not accurate. But just the idea that photons are absorbed by atoms, it's important. So some molecules, when they come together, they're able to absorb the light and keep it. Just the way the molecules are put together. Those are pigments. Not all molecules are pigments. You know, some molecules like water's a molecule. It lets light right through, right? Correct? It doesn't absorb light. If it absorbed light, it'd be dark. Water's not dark, it's clear. So clear molecules just let things go right through. Jellyfish, for instance, are made of a lot of molecules, and they're transparent because they don't have a lot of pigments. So pigments absorb the light energy. They absorb it. So what would be the pigment of light, what color would the pigment be if it absorbed all light?
Light.
That's right. When all light is absorbed, the color, and I'm going to put color in quotation marks, is black. Because black, some people argue, is not color, it's the absence of color. So true black. There's only a couple, I think we've come very close to true black. You can see it, you can play around with it. It's on, there's a paint that's made that's true black. It's very expensive, I think. You can look it up. There's YouTube videos on it. It's really an amazing substance. True black is crazy. I mean, it's something that you wouldn't even, it looks like, I have no way of describing it. It's really has something. You have to go on YouTube and look at it. Yeah.
So, Mr. Mendoza, what do people call it hyperpigmentation?
Hyper?
I heard that before, but I don't know what it is.
I'm not sure what that is. I wouldn't even worry about that. You know, people's obsession with skin color is just that. It's an obsession. It's a ludicrous. It's just ludicrous. Pigmentation, pigments in your skin are genetically bound. You inherit a certain set of genes. By the way, there's 6 genes involved in it, not just one. That explains why Europeans, English, British people are very pale, right? 2 British people could have a child that's black, and it's happened. And 2 black people, I'm using this word in quotation marks because I hate the word black and white or Caucasian. These are false words. They're words made up by people in basements, ignorant people in basements that did not know much of anything. It's literally, that's the history of the word Caucasian. I don't know if you know that. The word
Caucasian was actually people from like
the Caucasus Mountains, right?
Yeah.
Well, the reason that they chose that is they wanted to pick, the person who chose it was an ignorant individual who wanted to pick the lightest skinned people on the planet for the word Caucasian. That idea wasn't a bad one, I guess, if this actually existed, but whatever. He picked Caucasian because of Caucasus Mountains in near Russia. Well, he didn't understand this, but actually those mountains they have a lot of the population that lives there is actually Iranian. So their skin is very dark. So the Caucasus Mountains actually have a lot of dark-skinned, if you want to call people that, darker, more pigment than lighter-skinned individuals that might be, I don't know, Scandinavian or whatever. A better term for them might be Scandinavian, right? Rather than Caucasian. It doesn't make any sense, right? So again, ignorance. All this is rooted in ignorance, not in good science, not in anything that's been tested, data collected, and decisions made. That was not the case when these terms called race were developed. In fact, they're just full of ignorant comments based in lies and deceit. So I don't get involved with that hyperpigmentation discussion. I kind of focus on the pigment, right? The biomolecule that we're talking about. And as someone mentioned a moment ago, in humans, it's melanin. And the amount of melanin provided by a series of pathways called genes, right? Several genes being turned on or off, either encouraged having the transcription factors present or not, produce either a lot of pigment or not enough pigment, and you make it darker, or for instance, not enough pigment would be someone like an albino. That is the one case where you have a true recessive gene showing up, where that is the master gene for all the pathways. When that shuts down, there's no pigment. That person does not produce any molecule. That their skin is very transparent. So light goes through it, doesn't absorb. Skin doesn't absorb the light. So what you see, that's why they're very pink. Their eyes are red. The reason they're pink and the eyes are red is because you see the blood, the pigment of the blood, which is red, right? So, and they're very sensitive to light. They will burn very easily, and so they have to be very careful. They'll put sunscreen on, they'll get contacts for their eyes, and they'll usually wear hats or some kind of, their hair won't even take a pigment. It won't take it just because it doesn't dye well. So some people might wear wigs or what have you. So understand when we're talking about these pigments, it can be very important. And skin color is not relegated to this idea. This idea of race and skin color, they don't line up. Is that clear? There are people that are light-skinned that have many more African originated genes than, and there are people that are dark skinned that have much more European originated genes. So the idea of race and skin color just don't match up. So just you need to realize that. All right, moving on. All light is absorbed. Then the color would be black, quotation color, because it's really the absence of color. True black, I encourage you after class to go look it up on YouTube. It really is cool. They talk about magic. It's really like magic, the cool things they do with it. So if a pigment, for instance, doesn't, so we talked about an eye, so you're right. We have our retina has pigments, that collect certain, our eyes have pigments in the back of the retina. There's some pigments here in the iris to help help stop too much light from getting in. That's why people with albinoism don't need contact or sunglasses, because that too much light gets in. We have this color around our eyeball. The darker color absorbs more light. The pigment in the iris, the darker it is, the more light it absorbs, protecting our eyes more from the direct sunlight. So people from the Caribbean, people from so much more light. We need more pigment to protect ourselves from that direct sunlight. Where people from Scandinavia, they still need pigment.
It's not as much.
There's not as much because that light does bounce off snow. You can get sunburn off the snow. We can get what's called snow blindness. It happens to people. Oh. So you have to be very careful with too much sunlight, even in the north. But they need less pigment. Their pigments are lighter. They have less of it. Yeah.
So you saying like having brown eyes is better than having like blue eyes?
There's no better or worse. I don't like that term better or worse because it suggests there's too much suggestions. I would say to you, it depends on where you
Not
live.
better, but like-
It depends on where you live. Like if we were in Africa, if we were in the Sahara in Africa, I would want dark skin and dark eyes. In fact, if I were in the desert, I'd be wearing dark eyes. I'd have sunglasses on, right? And if I were in the desert, I would also have dark skin. I would have something called sunblock on, right? So I may not, I would not be there because I would not want to get burned. I would not want to get skin cancer. I would not want to get retinal damage. So I would certainly be appropriate. In fact, when you look at the highest place for skin cancer in the world is Australia. Why? Because Australia is a lot of sun. In fact, if you've seen the Aborigine, they have very dark skin and dark eyes. Why? Because the sunlight is really strong down there. So over the people that survived in Australia naturally are the people that have dark skin and dark eyes. Well, Europe in England took all their criminals and sent them to Australia, and they called it a penal colony.
Oh, wow.
That penal colony became the country of Australia. So there's a lot of Europeans down there that live down there, but they grew up, they evolved where? In England, right? Where the light is less direct. So their skin is light. Their eyes are lighter. And now they're in Australia where the sun is much more direct. So their skin color is still light, but they tend to burn. So you'll see a lot of redness in their skin. You'll see that a lot of their skin, a lot of people there get skin cancer. And the reason for that is in part that they evolved in one place and then moved to another. Over time, over thousands of years, if we did not have science, then that population would evolve again and become darker, right? But science kind of trumps it because you could use sunblock and you can use sunglasses, and that stops the negative effect of direct sunlight. So anyways, pigments absorb light. So what color would your eye see? If the sunlight is coming in, sunlight is white, correct? Mm-hmm. Sometimes it has a yellow kind of, depending on the angle of the light, might have a yellow tint. But by the way, white, what do you think is also not a color? I don't know if you knew that, but white is not a color. What is white? Yeah.
I was gonna have another question, but is it white every color?
That's right. White is all colors. Good. So white is all colors. Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv.
That's how I remember it.
That's how you remember it. Roy G. Biv. It's in that order, too. Now, I got to tell you, it's not all the colors. Obviously, there's millions of colors, but these are the kind of the main ones. There's arguments over Roy G. Biv and about how accurate it is. And then there's also, you can have, but this is the order. And light doesn't stop there, by the way. This is just the visible light. This is the light that we see. Snakes, for instance, can see infrared. When they flick their tail out, they don't just taste the air. They can see through sensors. They can see the infrared scale. So when you're talking about infrared, infra means under. Red, so this is red. The R part of Roy. Infra means under, right? So it's under red. So it's under red. So this is red, correct? Mm-hmm. And then we're going in this direction because things go from low energy, not low, but lower energy to higher energy.
You got a minute left in those.
It's not everything I wanted to talk about, but I think it's important that we talk about it. Huh? I don't know.
54? Oh, never mind.
How much time do we have left?
You got like, it's like 10 minutes.
Oh, good. So this is called ultraviolet. You've heard of ultraviolet?
Yes.
So ultraviolet's on this end, so it's above violet. And it continues. And you can get X-rays are on this scale, gamma rays. Gamma rays are all the way up here. X-rays, radio waves are all the way down here. There's numbers associated with them. But this is the part that's important to us because this is what we can see. Roy G. Biv are the colors every color we see, everything we see is in this box. Anything outside that box we can't see directly. We can see X-rays, but what do we have to use? Yeah, X-rays are radiation, but we have to, in order to see it, we need to see visible light. So we need we need an indicator. Just like pH, we can't see pH, right? So we need an indicator, something that changes color. So when we can't see X-rays or ultraviolet light or infrared light. So we need something that sees it, that reacts to it, and then leaves us a visible indicator. So infrared goggles, you've seen them on video games and movies. You put a goggle on, and you can see the infrared spectrum, but you're not seeing infrared. You're seeing the machines reacting to it, and emitting the visible light. Does that make sense? So we see the visible light that the machine puts out for us. So when you look at an X-ray, go get an X-ray. Do you ever see X-rays coming out of the machine? You don't see any X-rays because the X-rays are hitting you. They're there, they're hitting you, and they go through you, but you don't see them. There's a film or a machine, because now we use everything's digital, right? You have a machine or a film that does react to the X-rays and then changes them to visible light. So we can see what's there and what isn't there. But we can't see these things naturally. All right, so taking a look at pigments. So let's think about plants. What color are plants? Most plants on Earth? Green. Okay, so let's take a look at this green plant. What color do you think let's just ask this. What color do you think this pigment, the pigment in a plant, does absorb?
It absorbs green, it absorbs red, blue.
Red, that's right. Does it absorb green?
No.
No, why not? That's because of the color you see. That's good. So when light hits, light comes in as white because it has all the light. So it has R, O, Y, G, B, I, V, red, orange, yellow, green, blue, indigo, violet. What goes in, it hits the pigment. This pigment, by the way, I'm going to go ahead and label it for you. It's called chlorophyll.
Isn't that what causes us to change colors?
Chlorophyll, that's right. So there's a bunch of different chlorophylls. There's a chlorophyll A, there's a B, there's some other pigments called keratins. This is the pigment. Sorry. So the light hits Roy-G-Biv, and everything except green gets absorbed, this chlorophyll molecule. So light gets bounced back to your eyeball, and the color that you see is indeed green, right? All right? So when you see any color that you see, that pigment is absorbing every other color except for that one. There might be a couple colors. That's how do we get all these other colors then? We see red. How do we get magenta? How do we get...
Mix it with another.
We mix pigments that absorb different lights, and they reflect other lights, so that what you get is a combination of light colors, like red and, I don't know, brown makes magenta. I don't know what colors mix, but any color that's not red, orange, yellow, green, blue, indigo, or violet. Again, there's some argument over indigo and violet, but we'll move on. And the millions of colors that exist outside of that are colors that are mixtures of those that our brain interprets. And that's how plants work. That's how they absorb the light. So that's they absorb all that energy. They can do something with that energy. So let's go ahead and write down at least the photosynthesis major equation, and then tomorrow we'll get into the more details. So you're going to take water. So basically you're taking water plus CO2, and you're making sugar, and you're releasing excess oxygen gas. So this is what you take, the plants, this is photosynthesis. And this is taking in water and CO2, and you're producing sugar and oxygen. That's photosynthesis. Now let's just use the chemical equations. H2O plus CO2 yields C6H12O6 plus O2. And this is a gas, and this is an aqueous solution, and this is a gas, and this is a liquid, it's water. So there's your equation. Now we haven't balanced it though. We said we can't create or destroy energy or matter. Here's one carbon, here's 6 carbons. So how many of these do you need to make one of these? This is one carbon dioxide, has only one. There's no other carbon here, right? Only one C. Here's 6 C's. So how many CO2s do I need? I need 6. So I need to get 6 CO2. So I'm going to put a 6 in front of here. So let me zoom in. So I need this to be a 6. Ugh. I'll just write it out. Let me rewrite it. Blank H2O plus, I'm going to leave the state of the out, yields blank C6H12O6 plus blank O2. So I'll ask again, we said 6, right? So I'm going to go ahead and put 6 here. So what I like to do is when I'm balancing the equation, no, you don't have to balance the equation for this test or any test in this class, but you should at least be introduced to it, I think. All right, so here you have carbon. I like to list all the elements. Carbon, oxygen, and hydrogen on this side. On this side you have carbon, oxygen, and hydrogen. Here I have 6. Don't put stuff away yet. I know we're in a rush. Here you have 6. I'm sorry, I put the 6 in the wrong place. 6 carbons. Here you have 6 carbons. Well, how many oxygens is 6 times 2? 12. Plus 1 is 13, correct?
Yes.
So there's 13. Here you have 6 oxygens and 2 oxygens there, so that's 8. And hydrogens, 2 on this side, and there's 12 on this side. So we still got to balance these others. So how do we get? Well, the next thing I would suggest is we go ahead and try to balance the hydrogens, because that's an easy fix real quick. We can change this and this, changing this 6, which would change this hydrogen to 12. That balances the hydrogens, the 6 and 12, but now we have what? 6 oxygens here and 12 oxygens here. So now instead of 13, how many do we have? 6 and 12 is what? 18. Now we have 18 oxygens on this side. So then the hydrogens match up, the oxygens don't, and the carbons do. The easiest fix, if there's 6 here, how many do we need to produce 18? 6. If there's 6 here, I need how many to get to 18? 12. So if I just put a 6, if I just have 6 of these, then that gives me 18 on the other side. And now I'm balanced. So this is the balanced equation for photosynthesis. And when I say balanced, I mean now I'm obeying the laws of thermodynamics. I'm not creating or just, those of you that put away stuff and having conversations, wow. How about I put this on tomorrow's quiz, what I just said? That's what I'm going to do. So I'm going to put this on tomorrow's quiz. I'll ask you the stuff that I answered already. You guys figure it out. If you're paying attention, you know what I was just talking about. If you weren't, because you were busy doing whatever, then you don't know what I'm talking about. All right, guys, have a great day. Record this. All life on Earth uses ATP. This is how life deals with. This is one of the. By the way, this is kind of that always in the background. There's a question that scientists have always asked. If life is so different, they ask. If life is so different, if a bacteria is so different from a tiger or lion, if a cactus is so different from a human, how come we do all this stuff the same way? Why do all of us use DNA? Why do all of us use protein? Why do all of us take and do transcription? Why do all of us use ATP as a source of energy? Why is it that this is common among all life on the planet if we are truly separate creatures? And so the answer to the question, always it comes back to this, and why most of us feel strongly that it's pretty clear. Evolution is a fact. We know, by the way, evolution is a fact. The question is not, evolution is not in question. The connection between all life on Earth is not in question. Even creationists, people that believe they could teach God in a science classroom, which a lot of us don't think we should, even they can't disagree with evolution. It's just not, the evidence is too strong. So one of the pieces of evidence for evolution is that even though life is so different, we have these common functions, and one of them is using ATP as a source of energy. But there's a rule, and it's still on the board from last week, and those of you that didn't get it should write it down before you leave today. It's that energy cannot be created or destroyed. You can't destroy energy. You can't create it. We can't make it happen. The only thing that we can do is change it. We can change it from one form to another form. We can change ATP, but we can't create it. We can change one form. For instance, how does your vacuum cleaner, how does your car work? Your car takes chemical energy in the form of gasoline, it burns it, and it turns it into mechanical energy. It moves the pistons that move the tires. That's how your car works. The electrical system in your car, that movement of the pistons turns a generator that is connected to an alternator that switches the electrical AC current of that your engine produces and turns into DC current so that you can run your radios and your lights and all the electrical things in your car. So all we do is change energy from one form to the other. We do not create or destroy it. That's a fundamental law of all science. The first law of thermodynamics. Life has two ways of making ATP, of getting this energy. There's two ways of getting this energy. The first way is, I'm sure most of you have heard of both of these. The first is heterotroph. The other is autotroph. All right. Heterotrophs, they eat their energy. They ingest it. They have to hunt for it, search for it. We are heterotrophs. We all eat. There should not be a question. That should not be something would be like, oh, I wonder if we're heterotrophs. There should be a question. You eat. people, well, let's just go. Autotrophs make their own. They make their own food. They make their own food. Can they make their own energy? No, it's not possible. You can't make your own energy. You can only change it. You cannot create it or destroy it. So to get ATP, heterotrophs eat, autotrophs make their own. There's several kinds of autotrophs. Heterotrophs, I think it's easy. We'll talk about it. Heterotrophs do something called cellular respiration. That's it. That's what heterotrophs do. Autotrophs do two different kinds of autotrophs. There are those that do photosynthesis. So those are things like plants, yes, I heard someone say it. But there's also bacteria. And let's be clear, because I think somebody from the other class really embarrassed me when they said that animal cells are prokaryotes. Plant and animal cells are prokaryotes. They're not. Bacteria are prokaryotes. Or prokaryotes.
That's under the autotroph.
Yeah, there are some bacteria. So some, not all of them. Some are heterotrophs, but some bacteria are autotrophs. So some bacteria can do photosynthesis. Some plants can do photosynthesis. Not all plants do photosynthesis. There are some parasitic plants that don't do photosynthesis. They steal the sugar from other plants. There are vines that are actually parasites, but they're plants. There are some protists that are also photosynthetic. I guess some. Protists in plants are eukaryotes, bacteria are prokaryotes. But they exist, they do photosynthesis. So that's the main way that autotrophs make their own food, is photosynthesis. But there is another, it's called chemosynthesis. At the bottom of the ocean, at volcanic vents, where there is no sunlight, where no creature's ever even seen light, unless one of our robots had gone down there and shined the light. It says chemosynthesis.
No. Wait. Okay.
Chemosynthesis.
That's a KRC.
Where do you see this?
No, I'm talking about over there by plants and then this.
Plants, some bacteria are prokaryotes. These are karyotes. Protists mean the same. Some, I'd rather not say some. There's some protists that use photosynthesis. Some bacteria use photosynthesis. And most plants do photosynthesis. Is that clear? That's photosynthesis. We're going to talk about that in just a minute. Chemosynthesis, on the other hand, chemosynthesis is using chemicals in solution with some kind of heat source, usually, and produce ATP. It's a very specialized form of being an autotroph. These chemosynthetic bacteria are at the bottom of the ocean, in the middle, in the crust of the earth. They exist in places where sunlight doesn't shine, but they are there at the volcanic vent, and they are the basics of an entire ecology. You can go look it up, volcanic vent, life at volcanic vents, and you'll see there's a whole forest of tube worms and crabs that have no eyes, and all kinds of strange little creatures that are down there living off these chemosynthetic bacteria. Because as it turns out, and we'll talk more about it when we talk about ecology, they're all energy on on the planet has to start with the autotrophs. All life has to start. There has to be a base for the trophic levels of life. They all have the base of the life pyramid.
Can you go back in on the blue part?
No, I'm recording though. You leave some space and you can catch up later. Okay. I have to get going. So with autotrophs, the base of the pyramid is what another word that you guys probably have heard is producers. Have you heard of that? These are called producers. That's the word that you probably learned in middle school of what the basics of the trophic pyramid is. That's why they're called autotrophs. This is a trophic pyramid. This is where the energy flow is going. So this is the producers are at the base of the pyramid, and then what comes after the base? What is it? Anybody remember?
What was the question again?
That's right. It's a primary consumer, and then a secondary consumer, and that's what the little prime means, little degree sign, and then the tertiary consumer, etc. What do you notice about these boxes as they go up? They get smaller. There's a reason for that. Is because, as we said, we can't create energy, so we have to get, by the way, where do most autotrophs, we said it a minute ago, where do most autotrophs get their energy? The sun. So most energy is coming in the form of something called a photon. A photon is a quantity of light. It's actually a particle of light. Light has both wave and particle qualities. You know what a wave is, like a wave in the ocean. But there's also particles of light. And particles, light can act like little bullets. An example of a particle might be a BB gun or a pellet gun, right? Those are particles. I can sit there with an automatic BB gun and go and shoot hundreds of little BBs at you. Each one of those would be considered a particle. Well, the sun is shooting billions of these little photons down at us at all times. These little packets of light are what you see is just, it looks like that bright light is actually billions of these little particles flying at you. They're energy. Particles of energy. So they hit the autotrope. So here's the key, is that you're only able to capture 10%. So if this is 100% here at the sun level, then the autotrophs can only capture 10% of that. 10% of whatever hits them, they can capture. So they only get, if that's 100%, they'd only get 10. But let's start with the producers. So in this pyramid, every time we change, if we look at the 100% of the energy that we have in autotrophs, that means that all the rest of them are only every time it changes, you're only going to get 10% of it. So what percent is the consumer going to get of that 100% that's in the producers or autotrophs? So let me start again. The sun starts with all the energy on the surface of the planet, not including the chemotrophs, right? The chemotrophs don't need the sun; they do their own. But all the energy the sun's producing, that gets shined down on a plant. All the energy hits the plants, and all the entire planet, all the plants on the whole world, all together, can only capture a tenth, 10% of all the light that comes into contact with them. So this is actually only 10% here. This is 10% of the sun's energy. All right. So now that's all the energy that's available for life is in this pyramid. That's all the energy there is. There's no other energy that's available for us to continue. That's it. So this is 100% of the energy that's available. We have 100%. At the where? What level is that? At what trophic level is that? At the base, the first, or we call autotroph level, the producers. So at the base of the trophic pyramid this is all there is as far as life is concerned. Can anybody in here go outside when you're feeling low energy, go outside and stand in the sun and get all the energy you want? No, none of us can. What is the only thing we can do? Eat. That's all we can do. We can only consume. So everything other than this base, everything other than, oh, I can't believe that that's dying like that. I must have left it on. I apologize. Give me a second. So all the energy available to life on this planet is in the producer's genre. We're all good with that? Is there any confused point on that? No? All right. So that's 100% of the energy available. What percent then is available? What percent of that 100% can the primary consumers eat successfully? Actually take it into themselves.
8.
They can only take 10% of that. So the max that they can take, if there's 100 units, then the max they're going to be able to get on the primary consumer is 10. We are secondary. If you eat cows, you're a secondary consumer. What percentage do you get of all the energy that's available in the autotrophs? 1%. And the tertiary consumer would be like if a lion ate you. If a lion came in here and ate Ivy, he would be, I picked Ivy because she's asleep. Well, you have your eyes closed and the head down. So if the lion eats Ivy, what percent will the lion be able to get? Of the total in the autotrophs, what percent did the lion get? 0.1. So they only got 0.1. So if you got 100 units, let's get rid of the percentages so we're not getting all confused. If we have 100 units at the producer level, then the best that you're going to be able to get as a primary consumer, if we were cows, the best we could get of this 100 is 10. And the best that if we're human and we're going to eat cows, the best we're going to get is 1. So you need a lot more autotrophs than you have consumers. If you don't have more autotrophs than consumers, then consumers die. Because this is the amount of energy that's available, period. Yeah.
So worms be considered third prime consumers?
In this trophic level, it's confusing, but detrivores or organisms that eat dead things are part of they recycle everything back. They would get whatever percentage from, for instance, what I like to draw is I would like to draw it like this. She said worms.
Oh, those decomposers.
So they are decomposers. See, the problem with saying that they're primary, secondary, tertiary is decomposers take them all out. Decomposers eat depending on where if decomposers were taking from the primary, they can take from the secondary, or they can take from the autotrophs, because they will decompose all of them, right? And so so decomposers could theoretically have all of it if they ate all the plants. So, they can have all of the 10%. So they can either be as high as 10% if they eat the plant material. If they eat the primary consumer, they can get 10% of 10%, which would be 1, etc. Okay? Of the total that's in the autotrophs. So how much energy can decomposers have? It depends on what they're decomposing. So in any case, that's a trophic level. We're going to talk more about that when we get into ecology, but it's something you need to understand that energy is never created or destroyed. And every time you change energy, because that's all we can do, is you're going to lose most of it. 90% of it's gone. And you're only going to be able to keep 10% of that energy. So that limits us, which is why when you had that expert come in and talk to you about why is it better to eat the producers, the autotrophs, rather than eating the consumer, is that we have 100 units at the autotroph level, at the producer level. We only have 10 units of consumers. And even to have those 10 units, you have to have 100 units of plants for the 10 units to consume. And then we only get one. And the more of us that there are, the more of these you need, and the more of this you need. And we already don't have enough space to grow any more plants. Yeah.
Okay, so hypothetical. So if the cow eats the plant, and then we eat the cow, and then like the lion eats us, and then the hyenas come in and eat the lion, it would get 0.01% of the
Exactly right, yeah.
Wow.
They would get 0.01%, yeah?
Yeah, that's
Yeah. Could someone please, so yeah, every time, but when we say 0.01%, you realize that means that you had to have 10,000 plants to feed 5 cows. And then you need 5 cows to feed 1 human. Right? And then you need 5 human, or whatever it is, 10% all the way up. So the point is that where are you going to find, let me ask you this question, where is the most life on this planet? Where are you going to find it? Plants. It has to be here. It has to be here. If it's not here, you got a problem. It's over, right? We call it starvation. We call it mass starvation. Things start to die. What about this one? How many cows do you think you have? Which do you need more? More people or more cows? You need a lot more cows. You have to have 90% more cows than people in order to feed everybody a cow. Right? So I mean that's we can only get 10% of the energy from it if we're eating 100% cow. Same with anything that happens in a trophic system, because we can only take 10% out. Someone close the door of this bank. All right, so is it time to go already?